All right, so welcome to Math 383 Complex Analysis. And what I want to do today is I want to talk a little bit about Cauchy's formula and primitives, and emphasize a couple of things. The first is that we often have choices in how we complexify something, and depending on what you're doing, some choices work better than another. If a choice is not working well for you, what should you do? Yeah, choose something else, right? And if that doesn't work, yes? So one possibility is to choose something else. The other possibility is go back and maybe what you were doing initially wasn't so bad after all. Hopefully there's not that many choices, and with a reasonable amount of time, you can figure out which is the right one to do. What I really want to emphasize today as much as possible is we want quantities that are independent of the path that you take, because then it's very easy to compute. You just take the easiest path to work with. This is the same thing in calculating limits. If you can calculate a limit in, say, straight line, that's often significantly better than doing some kind of strange spiral drunken curve. But you need to know that the limit exists and is path independent. Once you know that, then you can actually compute it in any way you want. But you first have to know the limit exists and is path independent. The final thing is the level of rigor that we're going to do for something like this. So there's the old joke that somebody was taking their general exam at Princeton to get their master's, and the student was asked, can you prove the Jordan-Plain-Curve theorem? And their response to the professors was, can you? So risky strategy. It is one of those theorems that is intuitively obvious. If I give you a closed curve that doesn't intersect itself, the curve divides the world into two regions: the interior of the curve, and in the Shaka, it's the exterior, right? It turns out to be a little bit painful to prove this. The book does include a proof, I think it might be Appendix B. If anybody is interested in topology and questions like this, this is a great thing to look at. This is something that you are welcome to present to the class. It's an interesting exercise as to just how much detail do you want to get into to prove something like this. Now, when we are proving theorems, it is great to prove theorems in as much generality as possible. Why? Why do we want to prove theorems in great generality? Yes? In case you need them further down the road. It would be really great to have the theorem already there so you don't have to modify it. I remember I was refereeing a paper for a journal, and the reason they gave me the paper to referee was because the author quoted a theorem of mine, which was interesting because my theorem was actually a theorem of his from his PhD thesis, but he only calculated the main term. It's trivial to get the next term, and just because of the way publications things are done, my paper actually appeared in print before his was finished and sent off. And so I, of course, give full credit to him. The following is an immediate consequence of his work. It would have been nice if he had just calculated the lower order term, but he didn't need that for his application, so he just concentrated on the main term. Why? It made it simpler, easier to follow, easier to understand. So frequently there are choices when you're writing things up as to what level of rigor and detail do you want to do. If you prove things in such great generality, you often lose track of what you're trying to do because you're dealing with so many painful special cases and such general notation. It's often very simple to say, in all the applications I'm doing, I'm really only integrating along straight lines or arcs of circles. Let me just prove theorems in those settings. Okay. So what I want to do now is I want to talk about some consequences of Gaussat's theorem. So can somebody remind us what Gaussat's theorem states? So what do we get from Gaussat? Or Gaussat, I'm probably murdering the name. Yes. We don't have that from Gaussat. This is why I absolutely hate this part of the semester. Okay. We don't have that. Integrating along a triangle gives 0. And as an immediate consequence of integrating along a triangle, what do we get? Integrating along a rectangle is 0 if the function is holomorphic. We want to prove that what you said is correct, that if we integrate a holomorphic function along a closed curve, we get 0. And that's what we're going to try to prove today. So the theorem, I'm just trying to see why it's not. Yes, are you recording? It should be recording. I will double check. It is always, yes, I am recording. No, always ask. There we go. Right. So theorem. F is holomorphic on an open disk. Then F has a primitive big F, such that big F prime equals little f. Okay. We're actually going to prove this in a really nice way. We're going to prove this by constructing the primitive. So if we actually construct the primitive, then here's our function. So this is a constructive proof. As you are looking at this proof, you want to ask, where are we using the fact that F is holomorphic? Where are we using the fact that we are living inside an open disk? So sometimes, proofs have additional facts that just make the arguments easier. And sometimes they're there just for comfort. That we're just so used to saying it, we just put the language in. One of my professors at Yale, Peter Jones, always said, take any theorem in real analysis and remove a condition. If you remove the condition, it should either be much harder to prove or false. So for instance, if I remove the condition that the function is holomorphic, can we prove that it doesn't have a primitive? Or at least is there some function that's not holomorphic that doesn't have a primitive? We should be able to do that. So that would be a good exercise. What if instead of having a circle, what if we had a square, a rectangle? What if we had a donut? So a donut is very different than a circle, whereas you might say a square is very similar to a circle. So how much does the geometry matter? So here, I'm too lazy to use the insert circle command. So here is my circle. And of course, my circle is centered at the origin, because where else could my circle be centered? And if I needed to, what would the radius of my circle be? Well, I can always just rescale things if needed. So I have my circle. And what I want to do is I want to define the function f. So I'm going to take some point here, call it z, and I'm going to define a very special contour. And this is my path gamma of z. So f of z is going to be the integral along the path gamma of z of f of z dz. This is well defined. No matter what value of z you give me, I have a unique value big F of z that's now associated. Could I choose another path to get there? Absolutely, right? There's lots of different paths I could take. We would love to know that it doesn't matter what path we take. And in fact, we expect that is true. What theorem are we hoping to prove later today? Well, no, we want to prove in Gaussat's theorem. Cauchy's theorem, that it doesn't matter what path you take. Why? Well, Cauchy's theorem says if you integrate along a closed curve, you get 0. If I took any other path and run it backwards, I would then get a closed curve. And if the closed curve then integrates to 0, that means integrating along gamma of z is the same as integrating over the other path, and it would be path independent. So immediate consequence of this would be any other path should give us the same answer. Because we know once we have a primitive, then the integral of any function that has a primitive along a closed path is 0. So if can show this is a primitive, then we get the Cauchy theorem. The integral along any closed path of f of z dz equals 0. So if gamma is, say, gamma of z plus some other path, oh, that's not my computer. And I'm going to write it as this way, gamma tilde, to emphasize that I'm traveling it backwards. So here's my path gamma z, and here's some other path, gamma z tilde running in the opposite direction. Then the integral along gamma of f is equal to 0. So that will imply the integral along gamma z of f of z dz would be the integral along gamma tilde of f of z dz. That the answer would be independent of the path. So this would be a really nice result, that we don't have to worry about the path that we take. And maybe in some situations, we can take very easy paths. Just move horizontally and then just move vertically. Okay? Is that always going to be possible? If we're in a region like a circle or a square or a rectangle or a triangle, we should always be able to get to one point from another by just simple paths like this. And then you need to start thinking, well, what if I gave you a donut? You know, I might not be able to just move horizontally and then just move vertically. I might have to do a bunch of horizontals and a bunch of verticals. And does it matter if I start switching up the motion like that? So depending on the geometry of the space, the problem could become more and more interesting. All right, so we want to show that big F is the primitive or a primitive for little f. So what do we need to do? What do we need to show? Show big F prime of z equals the limit as h goes to 0 of the integral of gamma of z plus h f of z dz minus the integral over gamma of z of f of z dz divided by h equals f of z. If you want, I have probably slightly abused notation. Hopefully it's not confusing. Where's my notation potentially a little bit bad? Yes. I'm sorry? Okay, why is that bad? Right, gamma z is the curve from 0 to z by going horizontal then vertical. So gamma of z plus h would be the curve going horizontal and then vertical to the point, say, z plus h. And maybe z plus h is over here. Or maybe z plus h is all the way over here. We have lots of different possibilities for what gamma of z plus h is. That's not where the confusion could be.
That is easy because z is technically just a point.
Z is technically just a point. So what should I be using here instead of z?
Like an omega or something?
Yeah, like maybe a w for these places. Why? Because I've specified z as my special point. I shouldn't be using z as a dummy variable. Right? It's really easy to make small mistakes like this. Yeah, I'm just so used to using z as my dummy variable. And if I'm now using z over here, that could be a little bit confusing. So I should use w as my variable. Or instead of calling this z, what should I call this? Z naught. So I could do the z naught or I could do this. Either way is fine. All right, so we want to prove this. So let's look at what's going on. So here's the origin. And here's my path gamma of z. And here's the point z. And then let's say here's my point z plus h. And that's the curve gamma of z plus h. So if you look at it, notice we traveled the bottom segment, or at least part of the bottom segment, twice. And when we're studying, f of z plus h minus big F of z, that's going to be the integral along gamma of z plus h, say f of omega d omega, minus the integral over gamma of z of f of omega d omega. So the initial part over here, I'm going to subtract it off because really I want to travel this one in this direction. This is my negative gamma of z because I'm going in the other direction. I'm subtracting it off. So do we agree that that initial segment in the beginning is going to be canceled out? And so what we're left with is something that looks like this. Okay? Yes.
Could you just clarify why you got all in the conversation?
Well, because we subtract off the integral over gamma of z of f of w dw. So since we subtract it off, whenever you do an integral and you have a minus sign, you flip the order of integration. So we cancel off the beginning segment. So we now have a segment like this that we need to integrate over. But what do we know about a holomorphic function? What theorem do we know? Gaussat. So Gaussat tells us if we have an integral over a triangle or an integral over a rectangle, then it's 0. Boy, do we have something that's really close to being a triangle or a rectangle, right? We're just missing a side. Oh, that's not a big deal. So from this, here's what we have left over. Let's just add and subtract. So if we put this in here in both directions, we've added 0 because we're now integrating f of z along the same curve, but going in opposite directions so they cancel. And now, what is the integral over that square? 0. So now we can pass from this. So this is the same as just now integrating. Here is my point z. Here's my point z plus h. And I'm just integrating along that path. Right? What could be better than using Gaussat's theorem once in class? Twice! This is like, doing something L'Hopital once is not enough. Let's do L'Hopital twice. We love rectangles. We love triangles. Can you convert this to a rectangle or triangle? Yeah.
Add a hypotenuse?
Add a hypotenuse. Making sure you said hypotenuse and not hypothesis. Yes. So we can come down like this. And we can come back up like this. And that's a triangle. And so now it's the same as just integrating along the straight line from z to z plus h. And we'll call this path eta of z. If you want it, maybe it should be eta of z plus h, but hopefully it's clear what's been. So we've reduced the integral. So f of z plus h minus f of z is just the integral over eta of z of f of w dw, as f is holomorphic and used Gaussat how many times? Twice. And then we also said that some integrals cancel each other out. So the idea is you just keep winnowing away to make something very nice. Approximately, or can somebody tell me exactly how long is the path? What is the length of eta of z? Is the absolute value of h. So when we look at the limit for the derivative, we divide by h. Oh, well, that's essentially the length of here. It's not quite the length, it's a signed length, but that's fine. So we expect this integral to be small because we're integrating it over a small set. How small? It's got to be so small that when we divide by h, we still have something that's going to be nice. We get like our f prime of z plus something small. So hope f of z plus h minus f of z over h is equal to f prime of z times plus small error that goes to 0 with h. Going to 0. Yes? I'm sorry?
Small f.
Oh, sorry, yes, f not f. Thank you. Okay, so at least now we have an idea of what we're trying to prove. We've got an integral over eta of z. We know that it's going to be on the order of the length of the curve times the value of the function. How much is the function going to be changing on that path? H is small. Is the function going to change a lot? You would expect, in fact, that the integral of f over this path eta should be approximately f of z times the length of the path, right? Because the function really can't change that much. So let's consider the integral over eta of z of f of w dw. And again, here's my point z, here's my point z plus h, here's my path eta of z. So let's write f of w as f of z plus what? What can we write it as? So why could we write it as f prime?
Like f prime times b times.
So we could try to start writing it as, f prime of z times z minus w plus really small times z minus w. And we don't know exactly how small really small is, but it's got to be so small that as h goes to 0, the really small is going to 0 because this is a lower order correction because it's differentiable. It turns out we don't need something of this level. It suffices to use f of omega is equal to f of z plus, I want to try to use the same notation as the book. I think they use c plus c of omega with the limit as h goes to 0 of c of omega is equal to 0. What property am I using of the function? I'm not using differentiability. I'm using something a little bit weaker. Continuity. Just need continuity. Wait a minute. If I just need continuity, then why the hell was I assuming that f was holomorphic if I'm not going to use my f prime? Yeah, I used Gaussat's theorem multiple times. So for this step, I don't need to use holomorphic. For this step, it suffices to know that f is continuous. Earlier, however, I absolutely had to use holomorphicity if I wanted to invoke Gaussat's theorem. So because of the arguments earlier, I need to use holomorphicity, but over here, continuity is enough. So now let's consider the integral. So the integral over eta of z of f of w dw is going to just be the integral over eta of z of f of z dw plus the integral over eta of z of c of w dw. What's the integral of the constant f of z over the curve h of z?
Is it 0? Because primitive.
It's only 0. What does it have to be to integrate to 0? What kind of curve? It has to be a closed curve. This is not a closed curve. It's just f of z times h. So we're using, what is the primitive of the function 1? So what function, remember, w is my variable, omega is my variable, depending on how you view my handwriting. It's just w. So the primitive of 1 is w. So we get w evaluated at z and z plus h, which is just h. So the main term is just f of z times h. Now we have to integrate this. And now what we're going to do is we're going to look at how big can this be. So this is going to be less than or equal to the maximum of c of w times the length of eta of z. Right? I just take my integrand and I put in an upper bound for the integrand, and I multiply by the length of what I'm integrating over, and that will be an upper bound for this error. What's a bound for the length of the curve? Well, what's the length of the curve? We actually know what the length of the curve is. It's the absolute value of h. So this is just equal to the maximum of w on the curve of c of w times h. And what does that piece go to as h goes to 0? As h goes to 0, goes to 0. So even when we divide by h, this is still going to be small. So putting the pieces together, we have big F prime of z is the limit as h goes to 0, big F of z plus h minus big F of z over h. This is equal to the integral, so the limit as h goes to 0, integral over the curve eta of z of f of w dw over h. This is equal to the limit as h goes to 0 of f of z. We have h over h plus an error of size maximum c of omega times h divided by h. And so the first part is just going to give us f of z, and the second part goes to 0 as h goes to 0. And so now when we actually take the limit, we just get f of z. And so that finishes the proof. So the proof is just multiple applications of Grossat and the fact that we know integrals over triangles and rectangles to reduce to a nice curve. And so we only had to integrate along this really nice path, eta z. Here's z, z plus h, here's eta of z. And so we now know that we have a primitive. So f is holomorphic on an open disk. We have a primitive big F. So two things to note here. First, the primitive big F is defined constructively. Do you think there could be another primitive that works? Okay, what would that other primitive be? How would it differ? Yeah, plus a constant. I should be unique up to a constant. And if you think about it, if I have two objects and their speed is always the same, then the distance between them can't be changing. So the only difference could be is if they start at a different place. The other thing that's worth noting is this time I'm spelling disk with a K. How can you also spell disk? With a C. So depending on where you are in the world, they sometimes spell disk with a C or a K. Doesn't really make much of a difference. All right, but we now know that a function f on an open disk has a primitive, and we know if you have a primitive, then the integral along a closed curve gamma of f of dz is equal to 0. So now we have the beautiful Cauchy theorem. So the question is, where did we prove Cauchy's theorem? I'm sorry?
I don't follow the last line.
Okay, so we've shown earlier that if we have a primitive, then the integral over a closed curve is 0. We showed that earlier. And what we've just shown now is that if you're holomorphic, you have a primitive. Does this mean that the integral along any closed curve is 0? You have to be very careful right now about what we're using. It has to be in an open disk. If we are in an open disk, right? We just proved that if your function is holomorphic on an open disk, then you have a primitive. And we know earlier that if you have a primitive, then your integral along a closed curve is 0. So the question now is, for what other spaces? What if we consider something like this? So we don't have the interior. Do we have a primitive here? Yes.
We try and stick together a bunch of primitives.
So this is one of the things that you can try to do is we can take disks like this that have an intersection and just stitch it around like this as we go. The problem is, what must be true when you come all the way back? So if you're stitching your function and you come all the way back to the start, how should the value at the end compare to the value at the start? They should be the same. So consider z on the unit circle. And we'll write z as e to the I theta. We start here at theta equals 0. What happens to theta as we progress? It gets bigger. What's theta when we go a quarter of the way around? Pi over 2. We never use degrees. We always use radians because we want the derivative of sine and cosine to be related to each other. So if we keep going around, it's approaching 2 pi as we come back. And so if you look at the angle as you go all the way around, it's not continuous. Well, what do we mean by not? It's continuous, but then when it comes back at the very end, you've got two values at the same point. If I'm coming from, the slightly greater than 0, it's going to come down towards 0. If I'm coming a little bit below 0, it's coming up to 2 pi. And so we have some issues with this multiple valueness. And so we will have problems when we have regions like this in terms of how do we deal with it. So right now, we are not dealing with integrals like this. And we're not saying that a function that is holomorphic in a region containing, say, a donut has to have all of its integrals be 0. So for instance, I could have a function which is differentiable on the donut, and I could actually have it differentiable a little bit more. Maybe, here is my donut, and maybe I have something like this. So I have a slightly larger set, which includes, a little bit of the red on the outside and inside. But I do not include the very center. So I'll put in like a little warning over there. So the center is not included. So holomorphic in red region, not in yellow. So we do not know, if we call this gamma, that the integral over gamma of f of z dz equals 0. Can anybody think of a function that might be holomorphic in the red region, but not in the whole disk? Excellent. So consider f of z equals 1 over z. This is differentiable if we stay away from 0. And this function is not going to integrate to 0 along gamma. So we have to be extremely careful in what we've proved and how we use what we proved. So we've only proved that if the function is holomorphic in the entire curve and the entire interior. So we need interior, holomorphic inside. It's not enough to just be holomorphic on the curve and a little bit inside. It's going to be the entire inside. That's the real challenge. Okay. Now, in many situations, it's not going to be a big deal. What we can do is they call these, I think, the toy contours. Depending on what you did in multivariable calculus, you might have seen stuff like this before. So I could give you, we've talked a little bit about this, some kind of curve gamma. And I could give you, say, 2 points where the function is not holomorphic. And then what we would do is we would just modify our contour a little bit. So you would be coming like this, and we swing over, swing around, swing back, and continue. And we can do the same thing as we come over here. And what you'll see is that we're traversing those 2 points in the opposite direction you normally would. We're supposed to do things counterclockwise. We're doing these clockwise. So these are clockwise. And then you can start to worry, well, what if I have infinitely many such points and not finitely many? Am I going to have trouble? Well, it turns out if you have infinitely many points in a compact set, what must happen? If infinitely many bad points in a compact set, what must happen? They have an accumulation point. And if they have an accumulation point, then things are just going to go completely to hell. And so we really don't have to worry about that case. We only have to worry about functions that have finitely many poles, finitely many places where it's not going to be holomorphic. And as long as we're in that situation, we can always play little tricks like this. And we can make everything work out. And then what we can do is we can reduce the integral over gamma to the integral over these. And so what we get is the integral over gamma of f of z dz in this case would be the integral, let's call this point z1 and call that gamma 1. We'll call this z2 gamma 2. It would be the integral over gamma z1 gamma z2 of f of z dz plus the integral over gamma z2 f of z dz. And if we had more points where it blows up, we would just have more things like that. And the reason is that in this interior region, the function is holomorphic. And it's going to be holomorphic in the entire region, in the entire interior. In the interior. When we remove using the red curves. So we now get a new region where we can always define our paths and everything is going to be fine. If you want to think back to multivariable calculus, to the Stokes theorem, to the Green's theorem, we have a nice space where we don't have to worry about things. And so because of that, I can define my function. I can walk easily from any point to another. So the book talks about the need of a well-defined interior. And this is where the Jordan plane curve thing is coming into place. What might you worry about as we have more and more of these red points, red curves? Yes. Yeah, maybe some intersect with each other. And so can we do this in such a way that we're not going to have things intersect? And it becomes a question of just how much rigor do you want to have in proving something like this? So if I give you 6 points, can you show me that you can always have these slithers coming in such a way that they're not going to hit each other? Given the fact that we're not proving that a curve has an interior and an exterior and that's it, that it splits the plane into two things like that, I think it's fine not to go into this level of detail. And technically, we're only proving this in the special case where we can easily write down what's going on. So notice the problem that we had when we were trying to just continue in circles is not going to happen here. I can't continue in circles all the way around and get back to where I started. And so if I try to just continue in circles, and I try to go around like that, notice as I try to come back, what happens? If I have a wall, I can't pass through that wall, and that stops things from being multiple valued. So that's the reason this is all going to work, is that I can keep defining things like this, and I can keep running through the arguments. Okay, so let's talk about trying to do this in practice. So there's lots of different contours that we can use. The big ones that I used, big contours are the following. Some kind of rectangle, some kind of circle, a circle where we throw away a circle on the inside. You could also, of course, do this for a rectangle where we throw away something on the inside. A semicircle where we detour around a pole where it blows up maybe at the origin, or maybe we detour the other way so that we actually include the pole. Doesn't really matter. Sectors, part of a semicircle. I think that's everything. Right. So these are the main shapes that we're going to use. And these are enough to be of tremendous value in analyzing a whole variety of problems that are difficult. So this is incredible. It actually worked out perfectly. I thought around this slide is where I would be able to get to an example. And so it's already set up. So this is the example that's done in the video. You're integrating 1 minus cosine x over x squared from negative infinity to infinity. So the first thing you should ask when you see something like this is, does the integral converge? So for convergence, what do we need to worry about? So what are the convergence issues? There's two of them. Could explode somewhere. And what else? So if I want it to converge, it's not enough that it doesn't explode everywhere. Okay, but we're looking at this. There's only one point where it explodes. So as long as it doesn't explode, I need one more thing for the integral to be finite. I need some kind of decay. So as long as I have some kind of decay, we're okay. So exploding near 0, it's 1 minus x squared over 2 factorial plus ... divided by x squared. So we're okay. So near the origin, in fact, it's going to look like 1/2. Looks like 1/2. And decays like 1 over x squared, which is integrable. So we expect that this integral should be well behaved. Now, this is a challenging integral to do. Now, we need to remember some trig. So e to the I theta is cosine theta plus I sine theta. E to the minus I theta is cosine theta minus I sine theta. So from this, we get cosine of theta is e to the I theta plus e to the minus I theta over 2. And sine of theta is e to the I theta minus e to the minus I theta over 2i. So what we can do is we can replace functions like e to the z or cosine with each other. We can go back and forth. And so if I give you a cosine of x, I can replace that as an exponential. And so I can do cosine of x is 1/2 e to the ix plus e to the minus ix. So the complexification would be cosine of z is 1/2 e to the iz plus e to the minus iz. So when I look at something like that, I'm in good shape. I now have a nice function of a complex variable. I can try to integrate that. Now, when I look at the function e to the iz and e to the minus iz, I have to decide, where do I want to integrate this over? And so these are the different ways of doing it. So imagine I choose some kind of curve like this. And I've got e to the iz, or 1 minus e to the iz plus e to the minus iz over 2 over z squared. That's the function I want to integrate. Well, the problem is, what's going to happen as we get very, very close to the origin? What does this look like? So, well, we get 1 minus, we have 1/2. E to the iz is going to be 1 plus iz plus ... And the other one is going to be 1 minus iz plus ... over z. So if you look at this, the ones cancel, right? We have negative 1/2 iz. We have a plus iz, So it looks like those cancel. So that's going to be good. So this is going to look like, this is z squared. Order z squared over z squared, we're okay. So when we look at it like this, everything is fine. However, if you look at e to the iz, e to the iz is e to the I x plus iy. This is e to the ix, e to the minus y. E to the minus iz is e to the ix minus, I'm sorry, it's minus I x plus iy is going to be e to the minus ix e to the y. So if I look at what's going on in the upper half plane, if I look at what's going on the part of the semicircle, e to the iz, is that growing or decaying? As we go high in the upper half plane, it's decaying. We've got this e to the minus y. So this is decays like e to the minus y in the upper half plane, which we often write as capital H. But this grows like e to the y in H. So if I were to try to integrate it like this, I would have problems because one of them is exploding, one of them is. So maybe what I do is I integrate one of them in the upper half plane and one of them in the bottom half plane. But I've got to be very careful because it's only their sum, which is going to give me something good when I subtract. So this is what I mean about the issues that can happen when you try to integrate. I need to have some kind of decay on the top contour. I want to basically say, look, I've got a nice function and the integral over the top part doesn't really matter. So the integral over the bottom is just going to be related to how things blow up. So this calculation is done in detail in the book. It's done in detail in the lecture from last year. I want to just emphasize the high level, what are the issues going on here? And so I'll include in the email later today exactly where to watch for the details of this calculation being done. What I want to do instead is just emphasize why this could be a problem. It would be nice if we could just integrate one function. And we want to say that the integral over the top part is going to 0, so it doesn't really matter. Well, unfortunately, one of them is exploding. So this is not good. So what could we do? Well, we want to integrate 1 minus cosine x over x squared dx from negative infinity to infinity. Is everybody okay that this is the limit as r goes to infinity of the integral from minus r to r, 1 minus cosine x over x squared dx? Yeah. In fact, this is almost the definition of the integral. The only difference is instead of going from minus r to r, I should go from minus a to b, where a and b are two free parameters. I'm doing a very symmetric case, but that's fine. I am trying to be very careful and not do anything illegal. So this is the same as the limit as r goes to infinity, integral from minus r to r of 1 minus cosine x plus I sine x over x squared. True or false? Okay, why not? But sine is an odd function and x squared is an even function. So sine of x over symmetric region, doesn't that just integrate to 0? Can I do this? Maybe that no was premature. It has good decay, it's odd. What's the only problem with sine of x over x squared? I'm sorry? No, the I is fine. I can just pull the I out. Near 0, sine of x over x squared looks like 1 over x, which blows up. So this is a no. So what I can do is it's the limit as epsilon goes to 0, r goes to infinity, the integral from minus r to minus epsilon plus the integral from epsilon to r of 1 minus cosine x plus I sine x over x squared dx. Is that okay? I've just now thrown away that little bit near the origin. And in the limit as epsilon goes to 0, when I look at the integral of cosine, well, near 0, the 1 minus cosine x over x squared looks like a half. So I'm throwing away something of order, epsilon. As epsilon goes to 0, I get it back, not a problem. And now I can add the sign. And the advantage of this is this now, I can write this as 1 minus e to the I z over z squared when I complexify. And now notice when I do it this way, I only have one exponential. Right? We did one of the most important things in mathematics. It's the last thing before we end today. What did we just do? We added 0. So that's the high level of what we're doing and why it works. Is we added 0, and because we added 0, it doesn't change the value of the integral, but it changes which integral we end up doing. And now we go through, we roll up our sleeves, and we just actually do the integration. All right, so this is a good place to stop.